So what exactly is a derivative?
A derivative is the rate of change of a function or a point in a function.
So think of a linear function.
The slope of a linear function is constant. It doesn't change. The derivative of this function is how much the slope changes. Well, here the slope doesn't change. It's constant, right? So the derivative of a linear function is just going to be the slope. So let's say 3 over 1, so the derivative is just 3. So now let's look at a slightly more complex problem. How about a quadratic function? So in a quadratic function, instead of having a constant slope, like in a linear function, you have a slope that's constantly increasing. The slope is getting bigger by the same amount each time. Okay, so now what's the derivative of this function? We said before that this slope of a quadratic function is constantly increasing by the same amount. So the derivative would be a linear function, which constantly increases by the same amount. So now let's find the derivative of a point. But wait a second. For a point, there's no change. Okay, well, let's look at an exponential function. Let's say we have a point and an exponential function. Now let's zoom in on that point. And let's zoom in again. Wow, that is starting to look a lot like a linear line. Zooming in on a point like this on a curve is called local linearity. It's the idea that if you zoom in enough on a curve, then you have a linear line, which you can take a slope of and therefore find the derivative. Let's look at an example of this with a quadratic function. F of x equals x squared.
So let's say we're trying to find the derivative at x equals 3. Now we're going to zoom in, like the previous function, and find another point that's very close so that we can treat this like a linear function. To keep things general, we're going to call the distance between these 2 points delta x, the change in x. So if 3 is x, and let's say delta x is 0.01, that makes the second point 3.01, or x plus delta x. So if we're treating this like a linear function, then what is the slope equation for a linear function? It's the change in y over the change in x. So now let's label the y values for each of these x values. We can call the first one f of 3, and the second one f of 3.01. Now let's expand this slope equation. The change in y is y2 minus y1, and the change in x is x2 minus x1. According to this specific equation, y2 is 3.01 and y1 is 3. So those are both squared all over the x's, which is 3.01 minus 3. Now when you do out the math, you realize here on the bottom, this is just equal to 0.01, which is our delta x. Now if you do all the math out, you come to 6.01. That would be the slope or the secant line between these 2 points, 6 over 1. Wow, that was fun. Let's do it again. But this time, let's have delta x equal to 0.001, making those points even closer. Now we can use the same equation as before to figure out the slope. 3.0001 squared minus 3 squared over our delta x, right? 0.001. This gives us 6.001. That's funny, these numbers seem to be getting closer and closer to 6. I bet if we did this again with a smaller delta x, we would again get a number that's very, very close to, but not exactly 6. This means as delta x approaches 0, the derivative, or the slope, approaches 6. But delta x never actually goes to 0, right? Think of it like we're taking these 2 points and making them closer and closer and closer until bop, that secant line we had turns into a tangent line. Now, what mathematical concept lets us approach a number but not actually reach it? Let's see, delta x is approaching 0. What Well, I know one way. We can use limits. Okay, now let's go back and get that fancy equation. Let's see. It was y2, which is f of x plus the delta x, minus f of x all over delta x, right? So now this is our equation. This is called the limit definition. Wait, but where is delta x going? Oh yeah, to 0. This generalized function is used to find derivatives of a function. Once you find the derivative of a function, you can just plug in your x and get your derivative. Now let's use the equation we were using before, f of x equals x squared. Okay, so now let's adapt this generalized function for the specific function we're using. It would be the limit as delta x approaches 0 is x plus delta x squared minus x squared over delta x. Now, let's think about this. Delta x is approaching 0, so we could just plug in 0. That would be x squared minus x squared over 0, which equals 0 over 0. But no, we don't like that. 0 over 0, that's undefined. That's bad. Okay, let's do some algebra to simplify this. Okay, first we have to expand, then we're going to do some canceling out. Hopefully we won't end up with a delta x on the bottom again. And let's see what we come out with. 2x plus delta x. Now, if we plug in 0 for delta x, we get 2x. This means that the derivative of x squared is 2x. Just for a quick side note for some spelling, so derivative is spelled derivative and not derivate. I'm going to spell it wrong a few more times in this video. Just bear with me, okay?
Now, all the way back here, we said that the derivative of this function where
X equals 3 is 6. So let's test that and see if it's still true.
we calculated that the derivative of x squared is 2x.
Now all we have to do is plug in 3. 2 times 3 is 6, which is what we got when we were estimating. Yay, it worked! As you can tell, derivatives are really fun. Thanks for watching!